All right, good morning. It's still morning. Good morning, everybody. Let me post the code. Top hat code is 6623. Okay, that's the first thing. I'm going to share my screen. Okay, all right. So the first thing we're going to do, I just want to show you assignment number 3. Okay, assignment number 3 is similar in structure to assignments number 1 and 2, except instead of search algorithms and sorting algorithms, we're going to do matrix multiplication, which was part of the last lecture. Okay, just if we mute our microphones, thank you. Okay. All right, so in this case, you're going to use 3 different matrix multiplications. One of them is use whatever is built in. Now, in Python, you use a package called, it's not really built in that sense, but it means Python is coding it instead of us, right? It's called numpy, and I show you how to get numpy. So you just go down here, you can import numpy. Usually we say numpy as np, and then you just say np dot. All right. Simple multiplication is a multiplication algorithm that you learn in, linear algebra, which we also talked about. And then Strawson, which is the divide and conquer one, so that you're going to do. And again, you can, look, you can use online sources to get the basic code, and then you just clean it up and make it work and fit it into our structure. Okay, so the reason we did assignment number 1 together was to help get you started, but also to give you a framework, a template that you could use for most of the assignments in this course. Most of the assignments will fit into this pattern where you just sort of plug in the different algorithms. Something to keep in mind is that the matrix multiplication is generally an n-cube problem. Even Strawson's matrix multiplication is n to the 2.8, which is close to n cubed, which means you can't do n equals 10,000. Probably not going to work. All right, so that's why I said, try n equals 10 through 100 instead of, up to 1,000 or 10,000. If you find that 100, one of the people in this class, I know his computer works very quickly, so much so that it's not picking up the time it takes. All right, so if 100 works really fast, then you can try to push it a little higher. All right, so maybe, yeah. Okay, so that's the idea. Okay, same basic structure, just 3 different algorithms. And again, one of them you don't even have to code at all. You're just calling the built-in code. Okay, so where do I have that? Right here. Okay, so you're just calling the function from native mult, like when we did search and what we did find and sort. Okay, so that's your next assignment. Okay, so today we're going to discuss what's called a computational geometry, right, which is a important application area in computer science. It's important as an application area, but it's also good for study because it mirrors a lot of the things that we have already just seen in terms of searching and sorting. So it's nice to see the analogy, maybe an unexpected analogy that happens there. All right, so that's what we're going to do now. Okay, so what is a computational geometry? Computational geometry is a branch of computer science. It's design, analysis, and implementation of algorithms applied to the field of geometry. Fair enough. Okay, and as I just said, it also it has relationship with sorting, and it also, sets us up for some recurrence equations, which is an important topic in analysis of algorithms. Right. So these are some of the topics that we're going to discuss today. Lines and slopes, which is pretty easy. Okay, stuff that you could do even without this lecture. Points relative to a line. Maybe you do or don't remember how to do that from your geometry or trig courses. That will also be important in terms of the convex hull, which is later on today. We're going to discuss the closest points problem in 1 dimensions and then in 2 dimensions. And interestingly, they are very different. Bounding rectangle, which is if I have a bunch of points, how do I find the corners of that rectangle? And then we have the convex hull problem, which is sort of like a bounding rectangle, but it's more general. If I have a whole bunch of points, how do I make a polygon around the convex hull? And finally, we'll discuss an application to computer graphics, an interesting application, okay? Something that you probably, many of you use on a regular basis without realizing. Okay, so our first one is a very simple problem. Okay, this is a problem that, again, you've probably done in either geometry or trigonometry or maybe pre-calc, which is to find the slope of the line. Okay, so how do we find the slope of the line? So first of all, we need to check that the x's are not the same. Okay, if the x's are the same, then we have a problem and we just return basically infinity. Otherwise, we find the ratio of the difference between the y coordinates and the x coordinates. Okay, so that's pretty simple. That you probably would hopefully be able to do even if I didn't show you how. The next question is maybe less obvious. Okay, and that is, how do I determine which side of a line a point is on? Okay, so how many points do I need for that? Let me just bring up the chat box here. So give me 1 second. Okay, let's see if it'll stay there.
3 points.
I need 3 points, right? Because I need the 2 points that form the line, and then the third point, which is, you know, where is it? Is it on the left side of the line or on the right side of the line? Okay, so we have 3 points. All right, we're calling the points AX and AY. So those are the first, actually the point is called A, right? AX and AY are the coordinates of A, BX and BY are the coordinates of B, and CX and CY are the coordinates of C. And we compare this, this formula to 0. Okay, so if it's greater than 0, that means it's on the left side of the line. And if it's less than that, it's on the right side of the line. And that can be optimized slightly by moving this onto the other side. It just cuts out on the number of one operation. Okay, so again, this is an interesting question in general, but it also comes up in the convex hull because, again, in the convex hull, you're creating a boundary around a bunch of points, and I'll tell you why that's important when we get to it. But one of the things you need to do is figure out, okay, I just found the line. Is a given point on the inside or on the outside? So I have to be able to answer this question, and this is some code that will do that. Okay, next we have the closest points problem. So does anyone know what the closest points problem is? Anyone heard of that before? So if I have a bunch of points along the axis, the x-axis, how do I find which 2 points are closest to each other? So what would be a brute force approach?
For every point, go the distance to every other point and see it from the smallest.
Okay, good. Sounds good, right? So I have n choose 2 pairs, and I find the distance between each pair, and I use, you know, standard minimization. So if it's less than the min I had so far, then that becomes the min, and I keep doing that. So how long does that take? So when I did a master's in computer science at City College, among other graduate study, and I had a professor who used to, during the exam, this is in the days when people actually use blackboards, he would write the answers to the questions on the board. And it was amazing how few students actually understood that the answers were on the board. So I'm asking you a question, it's right in the slide. So maybe that'll encourage you to speak up. So what is the time complexity of this brute force algorithm?
N squared.
N squared. Okay, very good. All right, now we're going to look at another algorithm. Okay, there we go. Pre-sorting. So the question is, this is a strategy in general. Okay, where have we seen this before, by the way, in this course, where we used a pre-sorting as a strategy for making an algorithm more efficient? Pre-sorting means you sort the data and then you do whatever you need to do.
Search.
Correct, right? So all but the linear search required that the data be sorted. So again, if you just want to look for one thing, you don't usually sort it, but that is, if you're going to be searching a lot, then it makes sense to keep the data sorted. Also, when we did, the order statistics, right? So the whole point of the lecture on order statistics was that you don't have to sort everything, but if you really need to get, all over the place, right? I need to find the 5th smallest and the 10th largest and so on and so forth, then it makes sense to pre-sort the data. Okay, so if I pre-sort the data, I take my points that were on the x-axis, which were in no particular order though, and I sort them. So now where are the closest points going to be?
You only have to go in order and look at the distance to the next point.
Yeah, so I just have to compare each point to the next point. Okay, everyone get that? So now what's the time complexity?
O of n.
O of n, why?
You only have to go through each element once, so it's
I
linear.
only have to go through each element once, right? I always compare it with the one before it, and I take that distance, and if that distance is less than what I had, so it's O of n. Okay, it's an n-1 comparison to be more precise. Okay, something to think about. I don't think I put it in the slides, but it has shown up in old exams, is farthest points. Okay, so you can think about that, which is if I have a bunch of points in 1 dimensions or in 2 dimensions, where would I find the farthest points? If I did pre-sorting, by the way, how would I find the, well, let's just ask the question. Okay, so if I don't pre-sort it, how do I find the farthest points?
Just brute force again, except for minimum, and I do maximum.
Yeah, correct. And if I do pre-sorting, how would I find the farthest points?
The low and the high.
That's correct, right? I take the, the low and the high are the farthest points and take their distance from each other, subtract the x's, and I have the farthest, correct? Okay, so now we get to the closest points problem in 2 dimensions. And surprising, or maybe not surprising, it's more difficult than it is in 1 dimension. Okay, so let's start with the brute force approach. What do you think we should do?
For every point, just do, the square root of a squared, x.
So it's not for every point, it's for every pair of points, right? For every pair of points, we do what you were saying. We find the distance between them, right? Use this formula here, and we compare that to whatever we had before. And if it's less than that, we now have a closer pair. Good. And how much work is involved there? How many pairs are there?
Oh, then squared again.
Yeah, so it's a little surprising, but it's also n squared, right? So I have to do a little bit more work because now I am, taking the difference on the x and the difference on the y, and I'm squaring them, doing a square root. All right, so here's some code for that. And okay, so before we get to this, I have a question for you. So how did we find the distance? I think
Minus x2 squared plus y1 minus y2 squared.
and what, there was one more piece there, right?
The square root of it.
The square root of it. Okay. Here's my question though. So maybe I spoke too quickly. Do I really need this square root?
No, because either way, it's not gonna affect from the shortest and longest.
Okay, so yes and no, right? It depends, right? If we care about the distance, then we need the square root because you need the square root to get the distance. But as Ellie said, if I just really want to know which is smaller or which is larger, right? It's not gonna matter whether it's a square root or not a square root, right? So if all you care about is find the closest pair, like in the pseudocode here, then I don't really need to bother with the square root, okay? If I want to get the actual distance, then I do the square root, but I can do that at the end, right? Once I find my smallest closest pair or my furthest pair, I can get the square root at the end. All right, so that's a little trick, but it doesn't change the time complexity. So whether I use the square root or not, it's not going to change, whether it's n squared or not. But keep in mind, as we know from last lecture, all these things cost not money, but at least time, right? They cost operations. So as we saw last time, finding the square root is not, it's not just press a button. I mean, it is press a button, but there's work that happens behind the scenes. And we saw, three different algorithms for finding the square root, and they're not all the same time complexity. So we should not sneeze over the work involved in square root. It's something. Okay, now we get to a sort of cool algorithm. And this is divide and conquer. Okay. Yeah. Okay, it's by a guy named Michael Shamos, and it's divide and conquer. Okay, and there's a lot of wording here, but we have a picture. So let me describe it, and then we'll talk about the picture. Okay, so here's what you do. You take your two sets, right, or break up your set into two parts, left and right. Okay, left and right. And what you're tempted to do is say, okay, find me the closest pair on the left, find me the closest pair on the right, take the smaller of those two closest pairs and return that. Okay, what's the problem with it? I'm going to repeat that, okay? So again, we, take our set, we break it up into two parts, right, using our x coordinates. So anything that's on, on the smaller side of x is on the left, anything on the bigger side of x is on the right. We do divide and conquer, or some other approach to find the smallest on the left. Do the same thing on the right. We take the smaller of those two, and that's the overall minimum. What's the problem with that approach? Okay, it's sort of on the slide. It's in the middle of the slide, actually. Or you can just think about it. Problem is the middle. Okay, look at this picture here. Okay, so this line here, this solid line here, that's where we break it up into the left side and the right side. Okay, everyone see that? Now, we're going to look at all of these and find the smallest pair, but here's the problem. The problem is that there could be some that are along this line, right? What happens if you have something right there and something right there? This happens, by the way, in border countries, right? So you could have, two cities in the United States that are far apart from each other. But you could have a city in the United States and a city in Canada that are very close to each other, where you could, maybe even walk over the border right over there, go from one city to the other, right? So that's what's happening here. You could have some of the points that straddle the border, maybe not straddle, but they're, right near the border, and they're very close to each other. So you're going to miss them if I only focus on the smallest on the left and the smallest on the right, and then take the smaller of those two. So that's a little bit of a problem, okay? Because it says, oh, so what did we really accomplish? I still need to look at all the points that are near the border, and I have to evaluate them. Okay, so we're going to do some analysis here, and I'm going to come back to this page in a little bit. And we say as follows, okay? So how many subproblems do I have? You remember this? This is our master theorem. Okay, how many subproblems do I have? Say it one more time. Two subproblems. And how big is each subproblem compared to the original? Half. Okay, so it's half. All right. Okay, and how much work do I have to do before or after the divide and conquer? So this is where it gets a little hairy, right? We say, okay, well, half the points are on the left, right? Half the points are on the right. I need to multiply them because I have to compare each point on the left with each point on the right. All right, so n over 2 times n over 2, and I get this recurrence here. So we use master theorem to help us solve that recurrence, or at least to estimate the recurrence. We say, okay, a equals 2, b equals 2, c is the power of n, is 2. I take log b of a, log 2 of 2 is 1, versus c equals 2. And I use I think it's case 3 of the master theorem, but also depends on how it's listed, right? So I get order of n to the c, which is n to the 2, which is n squared, okay? How does that compare to brute force? Just checking all pairs.
It gives the same runtime.
It's the same. In fact, it's worse. Why is it worse? Because now you have all the overhead. So someone posted on the Slack, right, that they were getting a recursion error, right? They were getting a recursion error because their quicksort was doing too much recursion. So I don't know if there might have been a bug, but even if there's no bug, right, recursion takes effort. So there's a lot of work that's happening here that we didn't do in the other one. So in a sense, this is worse. However, it's actually better. Okay, let me show you why. Because there's an observation here. Okay, we're not going to prove it, and I hope you'll accept it. If not, you can Google it and learn more about it. But it turns out that if I have a line here, and I say how many points are close enough to that line within a particular distance, there can only be 6 points. Okay, so let me say that a different way, right? If I pick a particular distance, there can be at most 6 points on one side of the line that are within that distance to each other. Because if I put more points, then I'm going to actually get a smaller distance. And then I would have found them on this side of the line. Okay, so what this is saying is it's not really true that I need to check n over 2 points on the left and n over 2 points on the right compared with each other, because I cannot have that many points so close to the line, because if I had so many points close to the line, then I would have found a smaller distance on one side of the line or the other side of the line. So we're going to modify our analysis. So we still have 2 subproblems. Each subproblem is still half the size of the original subproblem, but now how much work do we need to do? It's 6 points on one side of the line times all the points on the other side of the line times 2, because I need to do this on both sides, right? So I need to do it each way. So that is order of n, right? 2 times 6n divided by 2 is order of n. And now I repeat the master theorem. So I say a equals 2, b equals 2, c equals the power of n, which is 1. And based on the master theorem, that's n log n. And when remember this, where have you seen this recurrence before? Not with the exact same coefficients, but merge sort, right? Because in merge sort, what do we have? We had 2 subproblems. Each problem is half the size, and we need to do the merge, which is at most n minus 1 comparisons. Okay, so this is just another example where we had a brute force. Then we had what we thought was going to be an improvement. It turns out the improvement was bad, okay, or the same as the other, but the same is usually worse because it means you're doing more overhead and more complexity for no gain. But if we then tweak that, if we think about it more smartly, more carefully, we realize that it is good. So we saw that yesterday also with Strawson's algorithm, right? The divide and conquer didn't look so good until we saw the tweak of Strawson. We had that with Karatsuba with the long integer multiplication, right? So that's a recurring theme in this course is, our first attempt at the improvement is actually not an improvement. But when we think about it more, it's good. All right, so here are some, I don't think you'll have an exercise on this computational geometry, an actual programming exercise, but here are some places where you can get code. Okay. This is divide and conquer closest points, fine. Okay, so if you want the code here, we have some code. All right, now we get to a randomized algorithm. So just to put this in perspective, first of all, what is a randomized algorithm? What does it mean? You have a monkey, type the code and you see how it works?
We take
What is a randomized algorithm? So it means you're using a randomized approach to making certain decisions. Okay, right? So what were some examples? I can think of at least 3, 2 of them are related to each other in this course of randomized algorithms just so far. We're up to lecture 6 if anyone's keeping track. BOGO sort. Okay, how did BOGO sort use randomization? Remember, it takes a random permutation of the data. It's a random permutation of the data, and it says, is it sorted? If it's sorted, great. Otherwise, it takes another randomized permutation of the data. Okay, so that's not a very good randomized algorithm. Anyone remember another randomized algorithm? Quick sort with a randomized partition is a randomized algorithm, right? We randomly choose a partition, a pivot point between the low and the high ends of the array. And then quick select, those are the 2 that are related, right? So quick select is also, it's like selection sort, except, it's like quick sort, except you only do one side or the other. We use a randomized approach to find the partition. Okay, so here's a randomized algorithm due to Michael Rabin, who was considered to be an expert in randomized algorithms. So many randomized algorithms from that era came from him. All right, so again, not every randomization is good, right? You wouldn't want to, if you're trying to get to Queens College for our exam, you wouldn't want to take a random walk to get there. You probably won't get there on time. So you have to know when to use randomization and how to use randomization effectively. So he says as follows: take the square root of n of the endpoints, right? I have endpoints in 2 dimensions. I need to find the square root. Okay, how long does it take to find the square root of endpoints? I don't know, whatever we learned about square root yesterday. Okay, now we're going to use brute force to find the distance for the square root of points. All right, so how long does it take to find the distance, the closest pair, using brute force?
N squared.
N squared. But what is our n here? Our n here isn't n.
The square root of n, so it's just
Square root of n, right? So we're taking the square root of n, squaring it, so that takes order of n time. Now, do we have an answer yet? No, we want a real answer. We don't want an approximation. If we want an approximation, maybe we could use that, but that's not what we want. So here's what we're going to do now. We're going to take our area and divide it into a checkerboard, okay? Into little boxes. How big are these boxes? So here's the key. They're going to be d times d, where d was the approximate minimum distance, okay? Now, what happens when we take our grid and we make it into these little boxes? Where are the points? So there are a few choices here, right? Some of those boxes won't have any points in them. Some of the boxes will just have 1 point, and some boxes will have multiple points. Okay, so we don't care about the boxes that are empty. Okay, we only care about the ones that have pairs of points in them because they could be closer than the D. Understand that, right? If I have 2 points in a box, in one of these boxes, so they may be closer than D, and we need to pay attention to that. In addition, based on what I told you before, where else do we need to look? Do we only care about within a box? Remember this picture? Hold on. What was the point of this picture here? Or even in this picture?
There's only a certain amount of points that could be a certain distance.
Okay, well, you're right. Okay, there's only a certain amount of points, so maybe this picture is more important here. Do I only need to consider, within
Over
my
grid?
box? No, I have to also consider adjacent boxes. Why do I need to consider adjacent boxes? Because, if I have 2 points in different boxes, but they're right near the border of those 2 boxes, then they could actually be closer than the D as well. So that's what this bullet point is saying. For each such fill D times D, use brute force to find the closest pair. The overall closest pair will either be inside a box or spanning adjacent boxes. So I don't just have to look within the box. I have to look at all the neighbors. How many neighbor boxes does a box have? Think about a checkerboard. How many adjacent boxes are there on a checkerboard? The max.
8.
8, correct. All right. So now I need to, okay, I have to iterate over all the box. I'm sorry, for each point, right? This is the work I have to do. For each point, I have to look at, the neighbors, the box and its neighbors. Okay. So what is this M? So how many boxes am I going to have? Right, I have at most N boxes, right? Because the boxes I care about, right? Because I only care about boxes that have a point, at least 1 point in it, right? And then I need to look at the neighbors, but there could be M neighbors. Now, how many neighbors do I expect to have? So we already said there are 8 boxes, but how many points do I have to worry about with either in my box or the 8 neighbors? So if you have a lot of boxes, how many do you think are actually going to be adjacent on average? Let's do some math. All right. So I have a D by D grid. All right. And I have N points. So how many points per box? So in general, you would expect very few to be in any given box, right? And maybe 1 on average. And, if I include the 8 neighbors, so maybe 2, 3, 4, right? I don't expect to have a lot of them all near each other. So on average, this is linear, okay? Let me repeat that analysis, right? So we say, look at all the boxes. Look at the number of points within a box and its neighbors. I expect that number to be constant. Constant squared is also constant. So it comes out a constant times N is linear. Okay, where have we seen an analysis like this before, where we divided something up to the point where each unit was constant? So even when we squared it, it was still constant. I think 1 place in the court, maybe 2. Bucket sort and maybe radix sort, right? That was the idea there, that we put stuff into enough buckets so that the buckets are small enough that we can consider them to be constant. They're not dependent on the number of items. And therefore, when I square it to use the insertion sort on each bucket, I'm squaring a constant number, which is also considered a constant from the perspective of analysis of algorithms, right? So this is a pretty cool algorithm. You should know, if you are curious about it, you read about it, you will find out that there are some sort of implementation technicalities. It's not so easy to implement this and make it work in average linear time, but it is a cool way of thinking about it, and it's another example of randomized algorithms. Okay. We move on to any questions on that? Okay, next one. This is a simple algorithm, but it also gets us mentally prepared for the next thing, which is not so simple. Okay, so I'm calling this the smallest rectangle, and what it does is it says, okay, I have a bunch of points in 2 dimensions. and I want a rectangle that contains the points. Okay, so how do I do that? So I have two arrays, and you know what? I don't even need that n there. Need that n. Okay. Okay, so I have two arrays, okay? Array one is x, it's the x coordinates of all the points, okay? Y is the y coordinates of all the points. Do they need to be sorted? Are x and y sorted? No. Not only are they not sorted, but it's not even really clear what it would mean to be sorted, because if I sort the x, let's say in increasing order, then I need to sort the y because the x and y's match up, right? X of 0 goes along with y of 0, right? It's a coordinate. So if I sort one, I have to sort the other. But if I sort one, it's probably not going to be the same, you know, it's not going to mean the y's are increasing order unless it's just one big line. All right. So assume that x and y are not sorted. So what do I need to do? I find the max of all the x's. Okay, so that's going to be the rightmost x coordinate of the rectangle. I find the x min. Okay, now we have a way of, you know, hiding work in programming. So how long does this really take, by the way, this max of x?
O of n.
O of n. So it looks like it's O of 1 because you just call something, but we know that not everything is like that. Just like when you call you know, dot sort in Python or C, it doesn't mean, oh, it's an O of 1 algorithm because I just, you know, called one function, right? When you do your matrix multiplication assignment and I say NP dot and I pass them two matrices, it doesn't mean it's an O of 1. It's still probably an N cube, but I don't know how they implemented it. Okay, so each of these is really behind the scenes an O of n algorithm, O of n, O of n algorithm. So you find the largest x coordinate, the largest, the smallest x, the largest y, and the smallest y, and then we print them out. Okay, so that's that. Now, the reason I'm interested in this is for two things. Number one, we're going to move on to the convex hull. Convex hull is a much more complicated algorithm, but it's the same idea. It's saying instead of having a bunch of points and I want to make a rectangle about them, I have a bunch of points and I want to make a polygon. Right? Do we know what a polygon is? Okay, so a stop sign is a polygon with 8 sides. A triangle is a, okay, the stop sign is an octagon, and a, you know, a warning sign is a triangle, and then you have a rectangle. But keep in mind that in a polygon, the angles are not necessarily the same, and the sides are not necessarily the same. Okay, so it's not, you know, it's not a regular polygon like an octagon, you know, that we have for a stop sign and so on. Okay, so what is this convex hull problem? Again, we have a bunch of points. We have a bunch of points, and we want to make a polygon. Polygon means the lines have to be straight. So this is not a polygon, that circle there. This is a polygon. Okay, and we need to enclose the points. All right, why is this a practical problem? Or where would this come up in real life? So anyone have a fence around their house or their apartment building?
Yeah, kind of.
Condos, okay, so you want to, when you make a fence, you want to make sure that everything, you know, that belongs. Let's say you have a good example. This would actually be not so much a house. Let's say like a gated community, right? Where I have a bunch of houses and you want to make sure that the gate, the fence goes around all the houses that are in there. So the houses may be in a nice grid formation, and then you could use the algorithm from the previous, you know, from this rectangle, but they're not necessarily in that shape. So here's a cool algorithm. Okay, the cool algorithm is you take a very large rubber band. By the way, here's another thing. Let's say you have guards and you want to know where to place the guards, or you have cameras, right? and they need to control the property. So you need to know what area to, to cover. So here's a cool algorithm. It's more of a gadget than it is an algorithm. It's an algorithmic gadget. You take a really large rubber band, stretch it out around all the things, and you let go. And what happens when you let go of a rubber band?
It wraps around all the points.
It contracts, and it will wrap around all the points, right? So if you use nails for the points or something like that, so it would form a polygon around that. But that is a gadget. Okay, I don't know if you can program for that. Okay, so here are a bunch of convex hull algorithms. We're not going to do all of them. We're just going to do, I think, one or two. Okay. Actually, I think we're just going to do one here. Okay, so it's called the quick hull algorithm. Okay, and before we go any further, I'll give you a hint. It was not named after someone named Quick. So the hull is from the convex hull. Why do you think it's called quick hull? Might be quick, but what else does that name connote?
Something to do with quick sort.
Something to do with quick sort. All right. So that is that's a hint. Okay. So here's what we're going to do. We're going to summarize it. Then we'll look at some pictures. Okay. So we want to find the boundary points. Okay. Once we find the boundary points, what can we do with those two boundary points? Okay. Point number 2 here. Use the line formed by the 2 points. How do you find a line from the 2 points? So in the first slide, I show you how to find the slope. Okay. So anyone know how to find the line between 2 points? Maybe we should go back and do that. So let's, I meant to include that. So let's just. Okay, so line, so this is slope. Okay. Okay, how do I find the? How do I find the line? Anyone remember? Forget code for a second. How do I find, what's the equation of a line?
Like the slope.
Well, it has to do with the slope a little bit, but how do we, so we do something like this, right? Y minus X. Sorry, Y minus Y1 over X minus X1, okay, is equal to the slope. Yeah. Okay, so what's the slope? Okay, I'm ignoring this this error case, okay, where it doesn't have a slope. Okay, so that's the equation of the line. Okay, so we could say as follows. So I could write it this way, right? I could say y equals like this, y minus y1 equals x minus x1 times this. Okay. And then I could say y equals y1 plus I lose something there? No. I lost something, right? Yeah. Okay, so we need to.
When you say X, do you mean X2?
No, when I say X, I mean actual variable X, right? Because equation of a line has
Oh,
to have
okay.
an X in it, right? So it's an actual X and this Y is an actual Y. Okay, so that's gonna be my slope. And then my Y-intercept. My Y-intercept is going to be Y1 plus, I can say minus actually. That's going to be my Y-intercept, right? Right, because it's going to be the Y1 plus this. Okay, so now I'm going to return. So Y equals plus M. What is my M here? I need to, in Python, you need to str it. That's my M plus the X. And then I need the actual plus sign. There. Plus the plus sign and the B. What is my B? My B is that. I think that'll work. It's going to say Y equals, this is the value of M, which is my slope, the actual letter X, a plus sign, and then the B. Okay, so that's the line. So we have slope and we have line. Okay, so now we'll go back to quick poll. Okay, so again, we find the minimum max, we find the max, we know how to find max coordinates. We find the line. Once we have those two coordinates, we compute the line of those points. And now look what it says. It says to divide the set into two subsets of points. All right. How do we get the two subsets of points? We want the ones that are on the left and we want the ones on the right. Okay. How do we do that? How do we determine if it's on the left or right of that line?
Use the function we did.
We do the function, correct. We do the function from the beginning of class. Okay. Then we need to find the distance from the line. Okay. Right. How do you find the distance from the line? So we have that. I have code here. No, let's put that in as well. Let's just do that. Take the point to the line. Okay. That. formula for that. Okay, I guess we could use that. Okay, so let's go back to our quick call. Okay, so again, we find the minimum maximum, we find the line, then we find, we iterate over the points on each side. I find the maximum distance to the line, and that's going to create a triangle. All right, so let's take a look at this picture here, so then you'll appreciate it more. Okay, so again, we found the minimum point is A, right? That's the leftmost point. Okay, it doesn't exactly look like that from the picture, but let's say it is. And B is the rightmost point, and we create a line here. All right, and then we find which point is the furthest away. So we consider all these blue points and the orange points. They're not blue and orange yet. Okay, I guess someone likes the Mets. Okay, so you take all these points on the left side of the line, the blues and the oranges, which are all the same color at this point, and we find the point that's furthest away. So using that distance function, we iterate over that distance function and figure, for all the points, we find out that C is the furthest away. All right, so then we say, we make a triangle, right? We have this triangle with this point, the endpoint A and the endpoint B, and we have a triangle. And we find out which things are on the inside, which are on the outside. How do we do that? So let's say we have this line here, CA, right? So we know how to do that because we know how to find this point now. We know how to find this point. We get a line. How do we determine if something is on the left or the right?
Yeah, the function.
Or whoever.
Yeah, use the function though.
Use the function from the beginning of class, right? So we determine, okay, so all the ones that are outside the line we're considering them blue. Basically, we're saying ignore them. So either you flag them or you delete them from the set. They're not relevant here. Okay, I'm sorry, I said it backwards. Right, the blue ones are important. The orange ones are not. Why are the orange ones not? Because they're going to be already inside this convex hull. The blue ones are important because we need to figure out, how do we create the polygon around these points? These are remaining. The orange one's already taken care of. They're already inside the triangle, the implicit triangle that C, A, and B form. All right, so now we're going to do recursion. We're going to say, okay, I have these points here. Find me a convex hull of this piece. Find me a convex hull of this piece where this is one of the lines of the convex hull. And this is one of the lines of that convex hull, right? So we're just working through this here, okay? All right, so once we get that triangle, we said the ones on the inside, we don't need to consider anymore because they're already taken care of, they're already included, right? The ones on the outside we need to do using a recursive algorithm. So how is this like, can someone tell me how this is like quick sort? So you already correctly said that it has something to do with quick sort. That's why it's called quick call. But why is it? In what way is it like quick sort?
Creating a partition.
You're creating a partition, good. And then what do? So partition means you find something in the middle. I mean, not necessarily exactly in the middle. And you have the stuff on the left and the stuff on the right. In this case, we're not putting anything on the left. We're not putting anything. It's not like quick sort in that way. We don't actually partition the data in, we don't move anything. We're just determining what is on the left and the right. And then what do? That's like quick sort.
Recursively.
Yeah, we recursively process whatever's on the left and we recursively process whatever's on the right. Correct. Okay, so let's analyze it. Okay, that's what we do in this course. We design algorithms and we analyze them. So we're going to say that T of n is going to represent the work, the number of operations for quick call algorithm. We need to partition the points into left and right and O of n time. How do you know that that's O of n? Could someone, describe in pseudocode what we're doing here? So for each point, finish the sentence. For each point, what do we do?
See which side the line is on?
You decide which side it's on. So if you go back to that slide, I don't know if it's slide 3 or 4 or something like that, right? We run a function, very simple function to determine whether it's to the left or to the right. Remember, the function was called is left. So it's true or false. Okay. It is possible that it's going to be on the line itself. So we worry about that in the next point here. So we might need to adjust that is left, to actually have 3 cases, right? Is it on the line, above, or below? All right. And so now we have some of the points to the left, some of the points to the right, and then we have to determine what do we do with the boundary, which side do we consider it to be on? All right. So it's just like quick sort, right? We have k on one side, n minus k on the other side. And again, 2 points might get counted twice because you have to consider them both sides. I have a note here, okay? The note is an important note. It's saying that even though we're saying t of k, and even though we're saying t of n minus k, in reality, those numbers are going to be less because we don't use all the points. When we do the recursion, not all the points, some are on the left and some are on the right, but some get ignored. Right, the ones in the orange, we determine the ones that are marked orange are basically saying we don't use them. So they're not the TK, they're not the TN minus K, right? So those numbers are upper bounds, if you like. Okay, you can think of the TK and the T, it's really like a less than or equals. Okay, so let's analyze that. So the analysis for this is similar to the analysis that we had back when we did quicksort. Okay, as I said before, right? If you have a sorting algorithm, it often translates a new paradigm for sorting. It often translates for a new approach to solving other problems as well. So we say as follows, okay, I've got 2 subproblems. Each of them are half the size. This is a best case where everything works nicely, right? And O of n to do the partition, and that's n log n. Where have we seen this guy before? That recurrence. We saw it today even. We saw that in the divide and conquer for the 2-dimensional closest points problem. And at that point I said, well, what does it remind you of?
Merge sort.
Sort.
Yeah, it's like merge sort, right? Just change that there. Okay, like merge sort, all right? So we know merge sort by now. You should all know that that's n log n, all right? Fine. What about the worst case? I'm going to come back to the average. We call this a degenerate case, right? Where it sort of falls into like a bad situation. What is considered a bad situation here? In quicksort, what was a bad situation? What do you hope doesn't happen, but you can't really control it?
You pick one and everything goes to one side of it.
Everything lands up on one side or the other. So that's bad. Okay. You want it, somewhat evenly distributed. Again, you're not going to get a perfect distribution on average, but you like it to be, right? So that's why we had different techniques to try to help that along a little bit. Okay. So in this degenerate case, everything lines up on one side, nothing lines up on the other. And where have we seen a recurrence like this before?
Quicksort.
Quicksort in the worst case. Where else? Bubble sort, selection, bubble sort, selection sort, insertion sort, right? All those quadratic time sorts, they all have recurrences that look like this, right? You're removing one element and then you have to, solve the subproblem, right? With n minus 1. Okay, then we get to the average case. So remember how the average case works. You add up all the situations and you divide by the number of cases, which is it. So we iterate over k, where k is the number of elements on one side. And that k could be anywhere from 0 on one side to n minus 1 on one side, and the balance on the other. Okay, I'm going to fix this here. First of all, this is bothering me. Sorry. So let's just change that color to something more in the gray family. Let's try that. Okay, that's a little better. But more importantly, I'm going to do that. And I'm going to do that. Okay. Why? Why am I doing that? Because we said that in reality, I don't really get T of K on one side and T of N minus K on the other, because a lot of the points get thrown out, right? That's a worst case scenario. Okay. So that's it. How are we doing on time? We got a lot of time left. Okay, so here's what I'm going to do. We're going to work on assignment number, see if we can get assignment number 3 going for you, okay? So I'm going to stop my share. And what am I going to ask you now?
Share screen.
I am looking for a volunteer to share screen, correct? Who would like to be our volunteer? Everyone is so shy. Should we do eeny, meeny, miny, mo? Should we do a randomized algorithm? How about that? So 2 summers ago, it was during COVID. So my other college where I teach, they had a they ran their own internship program because no one could get regular jobs. So we had the students doing, I created the name, by the way, I was very proud of it. We called it LAVA, L-A-V-A. It stood for Laboratory for the Algorithm Visualization and Animation. And we had students writing programs to visually depict the algorithm and process. So the mentor, the head mentor, he had a spinner, a physical spinner, and he would, no, I'm sorry, it was an algorized spinner. It was a computerized spinner, and it would spin around, and it would pick, so you inputted all the students, and then it would spin around and it would pick a student. So should I do that?
I can volunteer.
All right, thank you. Who's that, Alan?
Yes.
All right, thank you, Alan. Okay, do I need to enable the screen sharing? Maybe I need to enable the screen sharing. All right, so bring up assignment number 3.
Number 2 and number 2.
No, 2, you're on your own.
I
When is 2 due? Is it
today.
today? Okay, I'm gonna put up a Google sheet, a Google submit form for you, okay?
Wait, I think you already did, no?
It's what?
Because I think I already submitted.
Well, you'll submit it again, okay?
Maybe what was the submit form that was in the bottom of assignment 2, like the Google Docs? Because that's where I did mine.
That's old, so I'm gonna ask you to submit it again, okay? Because I wanna break out the output into separate uploads, so it'll be easier to find stuff. Okay, so I'll give you another day to submit it since I didn't post the link before. Okay,
Well, assignment 2.
we are on assignment. Well, I'll give you another day to just submit assignment. When is it due? It's due today?
Yeah.
Yes.
So I'll give you till tomorrow so that you have a chance to use the new Google link. Okay, so what are you doing here? You're doing assignment 3 now, right?
Yes.
Okay, so just copy the whole thing. Okay, either way. I would copy the whole thing because again, the structure is almost the same. Just do Control A, Control C.
This is assignment 1. Okay, copied.
Either way, either way. Okay, go to the top. Okay, change that empirical. You need an extra I in there, an empirical. And instead of sorting algorithms, you could say empirical analysis of multiple matrix multiplication.
Of multiple.
Matrix multiplication. Okay, good. All right, so instead of a random list, we're going to call it random matrix. And I give you a signature there, so you could just copy the signature. Okay, and it's a one-liner. You don't even need matrix equals, you could just say return. Well, return and the code. Yeah. Except you don't need matrix, right? We don't need an intermediate variable. Okay, good. One down. Okay, let's, this will be helpful to, function to print a matrix. Okay. So you can click that, and there's some code there you could use, or different codes. So you could grab that line there with the join. No, go up. Let's do the one-liner. That line there with the print, you can grab that. Okay, you could put it into one big line. Okay, and fine, except we don't have an A here. We have matrix. And if you don't mind, instead of item, let's use the proper terminology. We don't call them items in matrices, we call them element. Okay, for those who aren't familiar, that curly brace :4 is for like a minimum position of 4. Okay, so before we go any further, you could delete some of these searches. So just keep one there. Keep one just as a structure. Okay. And if we go back, let's go down to the bottom now. Okay, let's move all this code into, okay, instead of searches, let's change that to ALGS, ALGS. Okay, and we're just gonna have 3 things. We're gonna, what do we call them in the assignment?
Matrix.
You know, but what were the names? So we had
Native mode, simple
native
mode.
mode. Okay, so if you
custom
want to put those in the list. Okay, good. And let's create dummy functions for now. I'll just put pass inside. So go up. The first one we can actually do because that's really easy. Okay, so you could say def native mode. What did you do there?
Say native modes.
Mult, M-U-L-T for multiplication. Line 20. Okay. Let's just code that one. Okay, so that one's a real easy one. So you need to import. You probably don't have an import already. Go up to import on the top, expand the import. Okay, we're going to import numpy. If you don't have it already, you'll need to actually install it. Numpy as py, as a np. Numpy, N-U-M-P. Stands for numbers pi, right? N-U-M-P, N-U-M-P-Y, numpy. Okay, and click on that. Is it installed already? You have it installed or not?
I think so. I don't
Okay, as NP, numpy as NP. Okay, good. So now we can do the native mult. The native mult will give you the code for it. Oh, no. No, I have the code there. Go back. Right there. Return, just say return. You need to return it.
know. Return this line, right?
Yeah. Okay. And let's create stubs for the other two. You could actually write that one also. That's pretty easy. So you could click on that link.
This one, right?
Yeah. It says C program, but they have Python also. You don't need the whole thing. You just need the actual code.
This one?
The actual code. So you don't need all that creating the matrix stuff. You just need the range. You don't even need to print it.
So this line.
You don't even need that. Just the computation. Oh, I'm sorry. No, I take that back. No, they're initializing it. Okay.
For me to scroll down?
You could grab that, but we should really do that. Okay.
It's,
Okay. You could
Yeah,
grab. There we go. There we go. Grab that from the res. Okay. Fine. Paste that into simple mult. Okay. So instead of calling it res, let's change the name to M3. M3. Okay, and move that 4 onto the previous line.
this one.
No, the 4 in the list comprehension, line 28. Move that. Don't need to put it on a separate line. It'll just be line
So it's
28.
that.
Line 28. Move
Okay.
that onto the previous line. There you go. Okay, now we don't have the N2. So N2 is the size, okay? So you could just say,
So M2?
no, it's not M. They should both be N, actually. So you could say, okay, you could say this. So rows above line 26. Above line, I'm sorry, after line 26. Now put that back. You're going to say rows equals. Okay, so the number of rows in the product is going to be the number of rows in the original, which is going to be M1. You could say len M1.
So
Len of M1. Yeah. Okay, good. And the number of columns. Cols equals len of M2 bracket 0. Okay. Fine. And now the range is going to be, the X is going to be cols. So instead of N2, you say cols.
You also?
Yeah, and the other one should be the range of rows, I think. Okay. And let's update that.
Change this.
Yeah, that'll be M3. I think for I in line 30 should be rows. We might have some things backwards here.
Yeah, it's M1, I think it was before.
No, but I don't know why it's M1. M1 doesn't make sense. If that's the matrix. Oh, you know what it is? Because they're, okay, I see. They're M1 and they are using matrix 1.
Yeah.
And we're using, okay, fine. So you need to change that. No. Yeah, fine, that's good. And move that line onto 1. So 35 goes on the same line as, yeah, and change that to M1 and M2. Okay, you don't need those parentheses in line 34. Okay, and you can get rid of the binary search recursive now. And the binary search, get rid of all that. Okay, let's just clean up the plot time. Okay, so wherever you see search, say dict algs, make everything alg. So it'll be more generic and we can use it. So wherever you see the word, so change searches to, just type them. So change searches to algs. Algs, not else, algs for algorithms. So it'll be generic. So if you want to use this program next time, not algs, ALGS for algorithms.
Oh.
Okay, instead of searches, say algs. Okay, search num will be algnum. Okay, good. Next line, anything to do there? No. It's for alg in algs. Previous line, line 40. And line 42. Actually, in line 30, let's make that algnum because it's singular. I'm sorry, 38. Oh, it's a singular, right? It's
So change to
singular, algnum, ALG. Yeah. Okay, and runtime of line 47, let's just change that runtime of algorithm. Instead of number of elements, let's say size of data. We want to try to make it generic, so next time we don't have to change as much. And let's pass in an argument into plot time. Pass another argument into plot time. Add one more argument, call it trials. And then in line 49, instead of hard coding word 10, let's do time for a quote. Time for a quote. And I don't erase everything. Okay. Time for a quote. Time for a quote. Listen to me. Time for a quote. Now, don't erase everything. Just listen to me. Time for, put a quote. Good. Plus. Double, you need a double quote because it's plus. Not two quotes, one. Plus STR plus STR. Okay, STR will convert a number to a string, parentheses, trial. So we don't want to hard code the word 10 in there because some people will use 5 and some people use 1,000, right? Plus, quote, trials. Okay, and you can use the word trials that you have there and the MS. Excuse me. Okay, you can clean that up. Get rid of the 10 trials. Okay, good. And let's do this more generically. Let's create a variable on the top of the sign. Put a variable on the top of the program. Call it assignment number. ASSN. You can lowercase this variable. Assignment num equals 3. Good. And let's put that in the, when it saves the figure, let's use that. Okay, so go to line 52 and put that into your string. Assignment plus that's right. There you go. Good. Okay. Let's go to the main. Let's get rid of all that comment stuff. Okay, for the sizes, we're going to do 10 times I for I in range 1 through 11. Okay, so we're going to go for 10 through 100. It might be too much. Actually, for now, let's make it 1 through 2. 1 through 3, let's say 1 through 3, because we want to just get this working. And trials, we only need one trial really, because the data doesn't really matter. It doesn't change the time complexity here. Okay, let's fix up, go to line 59. Get rid of those spaces there, good. Get rid of the 60 and 61. Change dict searches to dict algs. Okay, line 61.
If you right click refactor, you can change them all at once.
Yeah, but this,
You like right click on it and then hit go refactor rename.
Yeah, refactor rename will also do it. So you have to be on something though.
I'm on, so choose.
You do it again.
Yeah, just place your mouse over that variable. We'll have a tip. You can just use it from there.
Just click it again. Just okay.
Maybe
No,
because
don't change the signature. Just click on it.
Yeah, it says create parameter.
I think it's because you already got rid of searches. Now it's Alex. So it
All
doesn't
right. Okay. So fine. Just
right click on like the search word. You can change that.
I'll
Off.
just do it manually. And this is Al.
Al. Yeah.
Oh, now you should be able to.
Al, did you come up with any resolution to the time?
No.
Any best practice? No, nothing.
Like
Okay.
I was able to run it on the school server.
Yeah, I don't want to go there.
Or assignment 2, like most of them took longer anyways.
Right.
Only-
Right. Yeah. This one should take longer. Right. We're dealing with an NQ.
Yeah.
Okay.
Well,
You got to change the search to Al.
sorry, but yeah, when I had like the size of 10, a lot of those took 0 time, like even the sorts,
Uh-huh.
but enough from there. It was fine.
I heard that there are some other time method you can use, like
Yeah, I'm
CPU
sure there
time.
are all kinds of things we could use. Yeah.
I tried looking it up, but they said that using like the time, like the one that we use was the most accurate.
I mean, that is the standard. That is the standard. Okay, wait, what are you doing there? What are you doing there?
It's adding an arrow here, so I'm just defining it.
Okay, so
as
you're
in-
creating a dummy? Fine, you can create a dummy. Let's do pass for now. Okay, search for search. Search for the word search. So you find whatever's still. Not algs, alg. Okay, we don't need, by the way, we don't need that. So you, in between start time and end time, in between, hold on, don't erase it. In between those, you just need to call alg. You could say, if you want, you could say M equals, or M3 equals. M3 equals alg of M1 comma M2.
Parentheses.
Yeah, it's a function. M1 comma M2, and in line 71, instead of random list, you could say M1 equals okay, random matrix. Okay, yeah, and you're going to use for now. Okay, we're going to pass in -1 comma 1
Oh, where?
in the random matrix. We're going to keep it with nice small numbers. -1 comma 1. And the rows is going to be, what do we say, size. Okay, and the second column is going to be size also. Now, after size, you need size again, because we're going to have the same number of rows and columns.
So remove this, true?
What? Yeah. Size comma size. You got to look at the parameters that you have, right? You don't and get rid of the other true also, right? You got to pass the parameters that we have in our function. Okay, we don't need IDX. Line 72, we don't need. We don't need 71. No, I'm sorry. What 72? We don't need the new 72. Good. We need to copy 71 though. So we need 2 random matrices. So Control D on that line. M2 equals. Okay. And we need to get rid of lines 78 and 79.
So this also. 78.
Okay, we don't need line 76. Okay, you could print M3 if you like. You could print M1, comma, sorry, print matrix, call print matrix. M3. And after line 71 and 72, you could print a matrix M1 and print matrix M2. Control D, yeah.
Maybe you want to put the end time before the print.
Yeah, it is correct. You want to print it. Yeah, do that after. Okay, no, not that, not that. No, he's talking about in the guts of the algorithm there.
This one?
Yeah, that should come out. We don't want to time the printing. Good call.
So we after line 80.
You could put it right out. Yeah, that's fine. It doesn't really matter at that point. No, I only need one of them though. Yeah. And change that search to alg. Okay, do we have the word search left? You don't need to print the dict searches. Get rid of the print dict searches, 82. Okay. And we need to pass in the trials in line 87. 87.
Trials or trial?
Trials. Okay, we have any errors? Go to the upper right-hand corner. Click on that. Let's see what we have there. So let's fix them.
Remove this.
I guess so. Okay. We need to put str around that because it's a number. We're not using that. Oh, okay. I'm not sure what to
It's
do.
an
but
S. Wait,
I'm
is
not
it
sure what
S?
to. No. It's
You're
call
crazy.
and range calls. That's like we need that call.
Okay.
Okay. All right.
To show it's not used.
No, but we are using it because it's our counter. I don't know how to get rid of that. What's that exit out? The same thing. Okay. What about that? Okay, because we haven't coded that yet. Okay, same thing, duplicated code. Let me see that duplicated code fragment. What's it complaining about there?
He probably has a different file, like assignment.
Oh, yeah. So it's basically telling you to, by the way, you can do that. So once we have this we made more generic, we can actually call assignment 3.plot time and use that in your next assignment. Okay, fine. Okay, so let's run this. Okay, let's fix the error. Oh, is that because of the, okay. Here, for now, go to Strawson. Go up to the Strawson one. And for now, say return, instead of pass, return. We're gonna cheat for now, okay? Return, what do we call it? Native mult. M1, M2. I'm not sure that that's the issue, but if we're calling it, we're going to need something. Okay, run it again. Okay, what is it complaining about now? List object has no attribute name. Click on the blue link. Oh, it's not. It should be alg.name. Okay, run it again. Click on that. Oh, we might need. It might be because it's,
Maybe the native mode doesn't
it's
return
because,
anything.
well, no,
It doesn't return anything.
it does, which one doesn't? The molt?
When you
Simple mode.
use the native mode in the stressing mode, maybe it doesn't return anything.
No, with the Strassens,
Let's just go down to simple mode. We didn't return anything.
oh, that could be a problem. Yeah. Return M3. Okay. All right. So it's a start. Okay, I think there might be some kind of issue with the sizes. Looks like we're getting that timing thing again. Let it run to 100. And then we'll stop. So, and go up. Change range 1, 3 to range 1, 10, 11. Okay, that matrix looks too big, so there's something going on there that's off. But okay, we have a good start here. We have a good start. Okay. What I would suggest is you might want to try this with a matrix where you know what the answer is going to be. So let's say use all ones. And you see what it looks like. So instead of a random matrix, go up. You could make another copy called a ones matrix. You could say all ones matrix. And then you could just say 1 instead of random.randint. No, 1, the number 1. For col and range. 1 for col and range. Get rid of the mn, mx, right? We're not getting random numbers. Okay. And now call that on the bottom. So comment out the call to random matrix. So Control D, Control D.
Wait, you said comment
Control
out?
D, Control D. Again. Okay, so comment out 2 of those. And change the other 2 to all ones matrix.
Professor, we tested -1 and 1 before. How do we get numbers like -7 and -9 and things like that?
Well, because I just had it in the range -1 to 1. So you can pass in whatever you want for min and max, but I wanted to keep the number. Oh, you're asking how are they showing up in the result?
Yeah.
Because when you multiply it, they get, they add up, right?
Oh,
But
yeah.
something doesn't look right here. Your array, okay, change it back to range 1, 2. Okay, so we know that in this case, our matrices should look like 10 by 10. Okay, run that again. Okay, so is that the product? Go up in the console. So that's 1. We should print, after you print the matrix, print a blank line. Go up to the, no, in the print matrix. In the print matrix, you can just do another right before the parentheses, do plus right before the parentheses. Right, plus quotation mark, /n, \n. Okay, run it again so we can see. Okay, go up. Okay, so we have our matrix of well ones. We have M2, which is go down. Our matrix of well ones. We're getting 10 because if you multiply all the ones together, you're going to get 10. That's good. Go down again. We have 10. How many? Wait, we should have
Yeah,
Should have-
3.
we should have 3 sets of 10, right? Is that what we have?
Yes.
Great. Okay, so we're going to stop here. You could start working on the Strawson. Okay. Start working on the Strawson, and the code that's in the Geeks for Geeks is in Java, but you can convert that, hopefully easily to Python. Okay. So, or you could Google. I'm sure you can find a Python version. Strawson's an important algorithm. So if you go down, it's not that. That's the plain one. Go further down. No, you go further down. So you have a C version and a C+ and a Java version.
So is this all?
They have a Python version here also.
You found a Python version of the Strawson, not the thing at the top.
Yeah, he's on it right now. Strawson.
Oh, it's right. Oh, it's right there.
Yeah, this.
Oh, okay, good. You know what it is? I originally looked on another link on the Geek site, the matrix, the plain one, because this is, okay, fine, even better. So embed that into your code. All right, so we're not going to do it now. You can
Change this to that.
what?
Change this, right? Because recursive.
Well, yeah, okay, we're going to stop here, but you can okay, you can call it recursively if you like. You can. Okay.
Do we have to know the mechanism behind it? Because it seems like
You don't need to know the mechanics of Strawson. You have to understand the idea that it's divide and conquer. You get you instead of the 8 expected subproblems, you get 7. That's what lines 53 through 59 are doing. You can get rid of the comments if you want.
I think this method requires a split method. Should I paste it?
Sure, absolutely. You might want to call it Strawson _ split because you could just say matrix split. How about matrix split? Okay, and you can get rid of the, I don't like their comments, but it's up to you. Just watch out because you got that double slash. So I don't know if the double, you might need to do a regular slash or you could try it, or int row. Just remember, you need to int it, okay? And feel free to get rid of any comments that you think are extraneous. Okay, you could, well, it looks like you might have gotten it. So you could call, run it again with not the random one. So we know what the answer should look like. It should be all 10s. Okay, so the problem is it's an array form right now. So you might need to, we could change that. Go up. That one's easy to fix. Where's the shape? So instead of shape, you could say matrix len of matrix. So the row, just do it in 2 lines, okay? Where'd you go? Where'd you go? Row equals matrix of len of matrix, row equals len of matrix. And col is equal to, or I prefer, okay, fine. Col equals len of row. No, I'm sorry, you can't do len of row, my bad. Len matrix 0. Len matrix bracket 0. Matrix. Okay, we might have it backwards, but we'll run it. Okay, where's that coming from? All right, I have to drop off because I have another class, but good job. You can debug. Okay, but you know that the answer should be all 10s. Once you get that working, so then you can switch to a random matrix if you want. But again, it's not really so important. What's more important here are the sizes. But it'll be more interesting with the random matrix. Okay, obviously the answer should be the same for all 3. If the answer is not the same for all 3, then we have bug. Okay, so we're going to stop here. Thank you, Alan. Okay, bye everyone.
Professor, I have a question.
Yeah.
So, assignment 1, I realized I didn't submit it. Like when I went back to the file, like everything was still there, and I submitted it yesterday. But I didn't press submit for the thing.
All right. Maybe send me a message in Slack. We'll see.
Okay.
Okay.
I sent you a message yesterday.
Maybe last night.
Yeah, like afternoon yesterday, kind of.
All right. Let me look at it. Okay.
Okay. Thank you, Professor.